this video, I'm going to talk about Pascal's triangle. Now, I'm not really going to explain to you how it's derived or where it comes from, really the theory behind it. But instead, I'm just going to write out the triangle itself. And then I'm going to explain to you the pattern. And then I will have you try to figure out, I will give you a certain number of rows and I'll have you figure out the next 3 rows on your own. All right, so let's get started. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4. Try that again. 6, 4. Oops, that's all right. Try to realign that. That way it looks more like a triangle. All right. So I want to challenge you. Well, first, I'm going to let you figure out the pattern on your own. And I challenge you to figure out the next, to try to see if you can guess what the next 3 rows are going to look like what numbers will fill the next 3 rows. And remember that each row has to have 1, 2, 3, 4, 5, 1, 2, 3, 4, n plus 1 numbers. So basically, this row has 1, this row has to have 2, 3, 4, 5. So that means the next 3 rows I have to have 6, 7, 8 rows respectively. And again, I encourage you to pause the video. Whoops! I encourage you to pause the video and see if you can figure that out on your own. All right, so I'm assuming that you had a go with it, that you gave it a shot. So here's the answer. 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, and 1. 1, 7, 21, 35, 35, 21, 7, and 1. Did you get that? If you did, congratulations. But if you're confused and you have no idea what I did, then fear not. I'll explain to you in just a minute. All right, so there are a few things that stick out to me. There are a few patterns that I notice. The first is that all of these ones, I guess I should do it in a different color. All of these ones are the same. You notice that? Going all the way down the pyramid, like the edge of the pyramid, or the outer, yeah, basically the edge of the pyramid. Going all the way down, all of these are going to be 1. Okay? The next thing I noticed is that you got 1, 2, 3, 4, 5, 6, 7. Oops. Here. And you also have 1, 2, 3, 4, 5, 6, 7. And this is really significant. I told you I wasn't going to get much into detail, but like I can give you like a brief explanation as to why this is and where the Pascal triangle is derived from. But anyway, just know that these 1, 2, 3, 4, 5, 6, 7 in succession like this is significant. All right. And then we can figure out the rest from there. So let's say you got 1. The sum of all of these is going to be 1. I wouldn't say the sum. Basically, it's 1 plus, and pretend there's a 0 on the other side. So 1 plus 0 is going to be 1. And then, so I can erase this. Yeah, might as well just erase everything else. But I'll keep the yellow tick marks for now. So yeah, that's basically like the outer bound of the triangle. And whoops, let me erase this too. I erased a little too much. 21, 7. All right. And then we can, let's enclose the bottom of the triangle. I mean, it goes on like to infinity, basically. It basically goes on to infinity, but for now, I'm just going to stop at 7. Okay, so let's go down each row. So you got 1, 1, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, and then, yeah, it repeats. 1 plus 5 is 6, 5 plus 10 is 15, 10 plus 10 is 20, and then it repeats again. 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, and then it repeats all the way till the row is done. And there you have it. Those are the first 7 rows of Pascal's triangle. Now, I'm not really the best at drawing, so it doesn't look, it might not be the best looking triangle out there, but it's still a very marvelous pattern, nonetheless. So in case you're wondering where Pascal's triangle comes from, it comes from the binomial theorem. Oops, that's an M. IAL and theorem. And over time, mathematicians throughout history, looks like I'm missing a tick mark here. Mathematicians have played around with binomial expansion. And they began to notice some patterns. Basically, the coefficients of each row or each of a certain degree will result in these same numbers that you see here. That's the pattern that they noticed. So let's say you have A plus B raised to the power of n. Then like let's say, and remember that anything raised to the power of 0 is 1. So technically this is to the 0th degree, and this is 1, 2, 3, 4, 5, 6, 7th degree. Does that look familiar? That's because you saw these numbers here, remember? 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4, 5, 6, 7. So basically that's it. You got 0, 1, 2, 3, 4, 5, 6, 7. And this is equals n, equals n, equals n, and etc. You get the idea. And so basically, if you expand a and b to the power, for instance, let's say you expand to the power of 2, then it's going to be a plus 2a plus 1. And it's going to be, and then so on and so forth. And it's a really marvelous pattern if you look at it, because it's actually a really marvelous, like a rather profound, I think it's one of the most profound things in mathematics. So you have each row, we'll back up. And I think it's marvelous because, oops, I accidentally erased a 1 here. Let's put it back here. It's marvelous because, you know, instead of having to work everything out when you're expanding a binomial, then you can just pull from a row, whatever row corresponds to this degree here. So if it's to the 7th degree, then you can just pull from this row here. 1, 7, 21, 35, 35, 21, 7, 1. Just apply those coefficients. And that's about it. And again, I'm not going to get into much detail now. It's just an overview, but it's pretty amazing. And it's even more amazing that all you really have to do is just choose any pair of numbers that are adjacent to each other, and then add them together, and then you form another row. And again, you could continue this on to infinity. So like you could do 8, 9, 10, and so on and so forth. I mean, you might eventually run out of space on paper or whatever to do it, but that's the beauty of the triangle. It just continues on to infinity like that, and it's a fairly simple, and deriving these numbers is a fairly simple and straightforward process. At least, you know, from observing these patterns here. The following the proof, I mean, proving it and then actually expanded binomials, that's another story.